Okay, so how to do two-sided tests from this section instead, where before we've been doing ones that were essentially one-sided. So when we're saying one-sided, I want you to think about when we're doing the standard normal curve and we're using one side of the tail because our alternative hypothesis has been stating greater than, or if the other side was shaded, it would be what was considered less than. Now, when we're starting to say two-sided tests, we're going to end up having the graph where both the left side and the right side are going to end up being shaded. So it's greater than and it's also less than. In other words, not equal to when we're doing it. Okay, so you already have this problem on your worksheet that I gave you for your section 9.2 alternate examples. So if you forget the problem, you can pause the video now, go through and read it, and then you can pull out the information. So we want to state what we're going to do first, because remember you have to do the four-step process. So the first part to state is we want to test the following hypothesis at the alpha equals 0.05 significance level, where P is the proportion of all expenses that begin with the digit 1 for this company. Okay, so we also have to write what our hypotheses are going to be. So remember we would have H sub 0 of P equals 0.301 because that inside the statement, that's what we wanted to get. Or you have the alternative hypothesis, which is P cannot equal 0.301. Now the reason how you know it's going to be 0.301 is because they want to know when it's significantly different from. Okay, if they had said greater than, then you would have the greater than symbol, or less than, it would be less than. Or if they say they just want to make a change, you would also have the not equal to symbol. So you have to be careful with how you're reading the problem. So then you have to go through and do your plan. Okay, the conditions that we all know already are if the conditions are met, we're going to perform a one sample z-test for P. Okay, random, it's told in the problem that a random sample of expenses was selected. Okay, 10%, it's reasonable to assume that there are going to be 3,000 expenses in this company's financial records. And then we also have to do large counts. So remember, large counts is n times the null parameter is greater than or equal to 10. So remember, n equals 300. Your null parameter you get from your null hypothesis, which here is 0.301 and is greater than or equal to 10. You solve the left side, so you get 90.3 is greater than or equal to 10, which is true. You also have to do your other large counts test of 300 times 1 minus 0.301 greater than or equal to 10. So you end up solving out that multiplication and you get 209.7 is greater than or equal to 10, which also works. So remember, if your conditions are met, now we can go down and we can actually solve for we can conduct the one sample z-test for P. So in order to conduct the one sample z-test for P, you have to find your P hat. So from above we can see that we are told there are going to be 68 of them that have results of the expenses that begin with the digit 1. We're doing a random sample of 300 expenses, so P hat, because of this sample, is going to be 68 out of 300, which is roughly 0.227. Okay, now you need to go through and you actually need to think about, okay, here, if I had my normal curve, I have my mean of, my go-to value of 0.301. I'm actually at P equals 0.227. Okay, and I'm shading everything here to the left. Okay, so if I go through, I now need to make it so that it's standardized, that it can apply to all of my samples that would happen. So to do your standardizing of your test statistic, so remember Z equals P hat, so 0.227, minus your null parameter of 0.301, all over the standard deviation of your null parameter, 301 times 1 minus the null parameter, 301, all over the all over your sample, which is 300. Okay, if you don't know the formula with the variables in it, don't put those, because if you mess up putting in the wrong variables, points will be deducted from your AP test. They'd rather just see you jump right into giving the numbers part. So now you could go through this part in your calculator if you want to pause it so that you can see. Pause it to make sure you get the right answer. So you're going to end up with negative 2.79. So essentially I'm taking this curve from just like up above, where I have my mean of 0, and now I'm at a z-score of negative 2.79, and that's where I'm shaded. These two areas here and here are equal. One's just using a z-score, and one's using the actual numbers. Okay, so remember you have z is negative 2.79. So now you need to find the p-value using that z. So you're really trying to find, the p-value, which is going to equal the probability of getting a z less than negative 2.79. Okay, so you go into your tables and you end up finding that the probability of getting a z less than negative 2.79 is actually 0.0026. Or you could go and use your calculator and do your normal CDF function. Okay, so here we have our p-value as being 0.0026. Now, the problem is, remember when you are doing a test that has the hypothesis as being not equal to, you actually have two parts on your graph that you have to find the area of. So here we would also have to find the area to the right that is exactly symmetrical to the area to the left. We would also have to do it over here, which we know that because it's symmetrical, if this z-score is negative 2.79, this is 2.79. So the two areas are going to end up being equal, so we can take this p-value and actually double it. So when we double it, we get 0.0052. Okay, so our p-value is actually 0.0052 when we're doing it. If you were to go in and use the calculator over here, you would go to your one prop z test, you enter 0.301 for p for your null parameter, n is 68, x is 68, n is 300. You choose the not equal to the null parameter, and you have to go down and you can click on, you can click on draw. You can click on draw. Okay, it's not going fast enough for me. Click on calculate or draw, and it's going to give you a different z and it's going to give you a different p, but they're extremely very close to each other. The calculator method is just more accurate than the using the tables method. So your last piece then is to do your conclusion. Remember, you compare the p-value to your alpha value of 0.05. Even though the alpha value is not given necessarily in the problem, we always end up using 0.05. So because the p-value of 0.0050 or 0.0052 when doing it by hand is less than the alpha value, we reject the null hypothesis. There is convincing evidence that the proportion of all expenses that have a first digit of 1 for this company is not 0.301. Therefore, the company should do a more thorough investigation of the company that they were investigating. So there could be fraud going on with that company. So the A, J, and L associates is going to want to make sure they go back and actually look at this. Okay, so that leads us into more, but why confidence intervals give more information. So remember from our conclusion from the previous slide, which is stated here, what might that real P or proportion be? That is, what is the proportion of all expenses that the company had that begins with the digit of 1? So instead, we can use a confidence interval from Chapter 8. So we want to find and interpret the confidence interval for the proportion of all expenses that begin with the digit 1 for the company in the previous example. You still need to do the 4-step process. So your state and your plan, you go through. You want to estimate the proportion P of all expenses that begin with the digit 1 for the company at a 95% confidence level. Okay, we use a one sample z interval this time for P, not a z test for P, to check if the conditions are met. We randomize by going through and saying, yes, we have a random sample of expenses. 10% is reasonable, and you can continue reading. And then we check the large counts condition to make sure that it works, where n here is, again, it is 300. And it ends up being your p hat, remember, was 68 over 300, which is going to be greater than or equal to 10. You also do this opposite of that is 300, and you would have 1 minus 68 over 300 would end up being greater than or equal to 10 also, so they all end up working. Once you have that, remember now you go through and do the do process. So here we're doing a one sample z interval. When you're doing a one sample z interval, instead, remember you want to use the formula p hat plus or minus z star times the square root of p hat, times the square root of p hat, and then 1 minus p hat all over n. Okay, so p hat we know from above is 0.227 from the previous slide. Plus or minus z star, you actually have to go in and get your z star. Remember, we're doing a 95% confidence, so you end up going in and getting what the z star will be for 95% confidence, which is 1.96, times the square root of 0.227 times 1 minus 0.227 all over our sample size of 300. You'll go through, you'll end up having 0.227 plus or minus 0.047, and you can go through and check the calculations so that you end up with an interval of 0.180 and 0.274. So that would be the range of possibilities that you would have for the numbers of what they ended up having, or the proportions for the expenses that begin with the digit 1 for the company at a 95% confidence. Okay, so you have your piece with doing the workout. Now you need to write your conclusion step. So your conclusion step, remember, is we are 95% confident that the interval, which we found above, 0.180 and 0.274, captures the true proportion of all expenses at this company that begin with the digit 1. So what does that mean? Does the interval from part A lead to the same conclusion as a significant test? And explain. So does that 0.301 fall in between these two numbers? No, it doesn't. So then that means that that number is not going to be in there. So yes, it does help us to lead to the same conclusion. Remember, we said the null parameter was 0.301. This value is not in the interval from our confidence interval. Therefore, it's not a plausible value for the true proportion of expenses that begin with the digit 1. It agrees with the statement from the one sample z-test for P that the company should be investigated for fraud. So this just helps to support your answer. You can use the one sample z interval in order to find the interval with it when you are dealing with an alternative hypothesis that is not equal to whatever the value is going to be. Okay, so I just put k there for a constant, but you can't do this whenever you have p is less than a constant or p is greater than a constant. This only works when you're dealing with using the not equal to symbol for whatever your p value is going to be.